Welcome to another video for General Science. In this video we're going to be discussing work and machines. So here are the questions that we're going to answer in this video. How do machines make work easier? How are work input and work output related for a machine? And just look at that keyword work. Okay, remember the equation for work is force times distance. So each of these work input, there's an input force and an input distance. Work output, there's a output force and an output distance. Okay, keep that in mind. And here are the terms that we're going to be looking at. All right, let's dive in. So actually, let me back up real quick. So this is a good time to pause this video and look at the keywords that you need to make sure and learn by the end of this video. Okay, all right, let's proceed. So I want you to think back to the last time you had to change a tire, a flat tire. Now, you may not have had to, maybe a parent or an uncle or something did, but just think of changing a flat tire. Okay, it's not that easy. Unless you're the Hulk, who, if you can lift your car up really quick with one hand and still be able to function with the other, it's not a problem. But since we don't have the power of the Hulk, we have to use simple machines. Okay, like our car lift here or our car jack. We have to use car jacks. So again, keep in mind the question that we're looking at. How do machines make work easier? Okay, that's the question. So there's two ways. Number one, it's by changing the direction of the force needed, right? So we want to lift the car up, but if you notice when you use a car jack, when you maneuver the lever, you're always pressing down, right? So you're applying a force in the down direction, yet the car jack is lifting the car up. So how do machines make work easier? By changing the direction of force, and also secondly, by multiplying the amount of force that we can input. So input force. This is the force that you input. Okay, so the force exerted by you. The only force that you're exerting is on that lever. Okay, so you press that lever down. It is multiplied by input distance. I'm sorry, let me back up. So the force that you exert is multiplied by the distance, the input distance, right? Remember I told you earlier when you're thinking of work, think of the formula for work that we discussed in previous video, work equals force times distance. So you're thinking of the input force that you exert multiplied by the distance that you exert that force on. And that distance is from the top of the lever all the way down to your finished position on that lever. That is the distance that we're multiplying. So it's that distance times the force that you exert, which is a very minimal force. That will be, multiplying those two will give you the input work. All right, so input force times input distance gives you input work. All right, so now let's talk about what happens on the other end of this machine. So this is where we are applying our output force. So the output force is the force that is exerted by the machine itself. And you'll notice that the machine has the ability to lift the car, whereas you don't. That means something has happened. The force that you applied and the input has been multiplied by that machine. So the output force is going in the up direction, right? Because if you remember, your input force is in the down direction when you're pressing down on that lever. Also, the output distance. The distance of output force, the output force has exerted. Now notice also that this output distance is much smaller than your input distance. Okay? So it's output force times output distance gives us output work. Okay? Alright, so a machine multiplies the input force and it's able to do something that you are not. Okay? So let's take a look at another example. Alright. Now, actually, before I show you this example, let me back up really quick. Right here. I want you to consider once again the fact that your input distance is much longer than the output distance that you get. The car is lifted up in small increments, whereas you're moving your arm in much larger increments. But again, the force that you're having to exert is very low compared to the force that's being outputted by the machine. Okay, this is kind of an inverse relationship that you're going to see. On the other example that we have here. Okay, so here's our other example. Okay, here's a rower. I need you to pay attention to his arms. Look at the distance from his beginning position there to his end position. That's maybe what, 2 or 3 feet, right? Now look at the oar at the end. You notice where the oar is being, its beginning position compared to its end position. Okay, so its beginning position would be right about here, and it ends right about here. So when you compare those two distances, the beginning position and end position of his arms compared to the beginning position and end position of his at the back side of the oar, or the output side of the oar. Okay, so the input distance would be his arms right here, which would begin right about here at his chest and end just outside of his knees, right? And again, if you compare the distance that the oar is going, which is beginning distance right here, and its end distance is somewhere over here, that's about 8 feet that the oar is being moved compared to the 3 feet that his arms are moving. So you'll notice that the input distance that he does is much smaller than the output distance of the oar. Okay, and then you think about that with our other example. Our input distance of the lever on the car jack was greater than the output distance, so the car jack was moving the car in small increments. And here, it's the reverse. The input distance is much smaller compared to the output distance of the oar. Now, consider this for a second. Let me play this again, actually. Okay? Consider the fact that the oar is spending a much longer time in the water, right? And because the oar is spending a longer amount of time in the water, that is requiring a greater force by our canoeist there, our kayaker. Okay, so in some ways you might say that it's harder to kayak than it is to lift the car with the car jack. Okay, and that has to do because of the inverse relationship between the input force, or the input distance, okay, compared to the output distance, right? So the kayaker only has to go a short distance in order to go a longer distance on the output side of the oar. Again, the output side is the part that comes in contact with water. The input side is the part that he is holding himself. So because the oar spends so much more time in the water, that requires him to exert more force. And that force is applied to the water in one direction, which pushes the kayak in the opposite direction, the opposite and equal reaction here, going back to Newton's laws. Okay? Okay? All right, let's move on. So again, I want you to think about how the dynamics of both of these simple machines. The oar is a simple machine and the car jack is a simple machine. Okay, but the dynamics are a little bit different in the sense of how much force is required to move each object. Okay, either you're moving the car or you're moving the kayak. All right, and it all has to do with the distance, the input distance compared to the output distance. Okay, so the person has to input more force on the kayaker end than they do on the car jack end. Okay. Okay, I hope this helped. If not, then we always have lecture, and you're always free to ask questions in class, or you can drop me a line at the bottom comment section. Okay? Thanks for listening, and good luck in your studying.